Let's look at a project that walks us through some technologies that are commonly used in data science, machine learning, and AI. A quote from Gemini: "A well-designed data science machine learning project establishes a solid foundation for successful outcomes by carefully considering data quality, feature engineering, model selection, evaluation metrics, and deployment strategies." Of course, data drives discovery. When we're working on a research problem, we first want to define the problem. Then we need to collect the data. So that's going to involve finding the data, or actually finding a way that we can collect the data if we want to collect our own data. Of course, in this project, we will look at some pre-existing data that's already been collected, and we will download it to our system. Then you prepare the data. There is almost always going to be some form of pre-processing that is required to prepare the data to get it in the right format for your machine learning or data science project. And finally, your data analysis. And so you've noticed we've already spent a lot of time working on this project before we even get to the point where we're actually going to analyze the data and start creating some information from that data. And finally, when our analysis is complete, we need to deliver the results. So how are we going to disseminate our findings? The project that I want to walk through today is going to use several technologies that are commonly used. And to do this, I wanted to use a public data set. So the problem statement I have here is, can we train a machine learning model to determine if an SMS message is spam? So imagine that you are creating an app that allows SMS messages, so text messages, and you want to filter out those messages that are spam. Can we train a machine learning model to identify which messages are spam and which messages are not spam? The data set that I'm going to use for this project, I have a link to here, the UCI SMS Spam Collection data set. This contains over 5,000 SMS messages, and each message is labeled as either ham, meaning it's a legitimate message, or spam. If you want to follow along with this project, there's a link to the data set, which you can go and download from here. If you are going to use this data set in any of your research, you should certainly cite the source. I have downloaded the data set already, so let's take a look at it. This data set is in a tab-separated format, so I saved it as a file with a .tsv extension. And then when I double click on it, my operating system recognizes this as tab-separated data and is opening it in numbers. I'm using a Mac, so numbers being the spreadsheet for Macs. And you can see that the data has a column called, it actually looks like the column does not have a header here, but the column contains either ham or spam. So this looks like the label. And then for each message, there's just a string of text representing the text message. I want to open this in a plain text editor. So I'm going to open this with Sublime, which is the text editor I like to use. And you can see that this is just tab-separated data. So each row, let me go ahead and turn off word wrap. So you can see each row has two items separated by a tab. So this is a tab symbol. The first item is looks to be ham or spam, which is what we expect. And then the second item is a string. So the string is going to be the SMS message, and then ham or spam is the label telling us if this is a legitimate SMS message or spam. So that's what our data set looks like. I have saved this as spam-sms.tsv, TSV because it's tab separated values. Typically, when we look at data sets, we have comma separated values or CSV. Tab separated values can be processed just as well. And if you use the correct extension, that helps your operating system and other applications specifically know what to do with the file, but it also helps you remember because we're going to read this file into a data frame and we need to know if it's comma separated values or tab separated values in our data. So CSV versus TSV is how we're going to know that without having to actually open the file if we save it with the proper extension. So when you click on the link and go to the data set and download it, you download a zip file, and then you can rename the text file whatever you'd like. But if you want to follow along with this tutorial, use the same name that I used. The tools we're going to use, of course, are Python, which is the main programming language for data science and machine learning. Pandas, which is a very popular library for data manipulation. We'll just get a brief introduction into using that if you haven't used it before. And then Scikit-Learn, which is the machine learning library for Python. So we'll use each of these technologies in this project. The project steps include data collection. So we download the spam data collection set and we save it to a file. Next, we're going to do some data preparation where we're going to use Pandas to load and explore the data and perform some basic data cleaning and pre-processing tasks. Then we will use Scikit-Learn, our machine learning library, to extract features from that data, basically taking our text messages and convert them into some numerical features that can be recognized and processed by the machine. Then we will train a model. So we'll split the data into training and testing data sets, and we'll try a variety of different classifiers using Scikit-Learn to see if we can classify the SMS messages as spam or ham for that machine learning model. Then we want to evaluate each of the model's performance because ideally we want to find the model that's going to work the best. And so that's why we're trying multiple models, and we can evaluate their performance using several common metrics. In this case, we're going to look at metrics like accuracy, precision, recall, and the F1 score. And finally on this page, there is a sample implementation of the code that we're going to walk through in this video. And you can copy that and save it to a text file and run it directly. But for now, let's walk through the components of this implementation. So I'm going to pull up my text editor. You might be using an IDE for Python. I prefer to use a plain text editor that does code highlighting. So I use Sublime, which is going to provide some code highlighting. And then when I want to execute my code, I simply execute it at the terminal. If you're using an IDE, you probably have an integrated terminal and text editor in the same app. I like to keep them separate. I use Sublime for about a dozen different languages, programming languages and markup languages that I create different projects with. Of course, Python being a programming language and Pandas and Scikit-Learn being libraries for that programming language, it does not matter which particular tool you're using to implement your project, the code will remain the same. So let's start by importing Pandas. When we import Pandas, you will see in tutorials across the web, including the documentation on the Pandas website, that we commonly import Pandas as PD. Now that is not necessary, but that is a common standard. So now when I want to use any of the functions within Pandas, I don't have to type Pandas, I can just type PD. So the first thing I want to do is load my data. I'm going to load the data into what is called a data frame. So we've talked about different data structures before in Python. We have data structures like lists and dictionaries and tuples. Pandas is another type of data structure that is optimized for doing calculations, specifically row or column-based calculations on data. So it's optimized for data manipulation tasks. And the underlying data structure itself, if you want to visualize it in your mind, actually resembles a table with rows and columns. So we want to load the data into a data frame. DF is a common convention for naming your data frame. Of course, you can name it whatever you'd like. That's just a variable name. So I'm going to say data frame equals, and then I'm going to use pandas. So I'm going to type PD for pandas because I imported pandas as PD. And now I can use a pandas function, and pandas has a read CSV method. I'm going to use the read CSV method of pandas because I'm going to read that tab separated value file. I can still use the read CSV method with my file name. In this case, I have, let's see, I have my Python file and my TSV file in the same directory, so I can just directly state the name. Of course, if I have these two files, my Python file and my TSV file in different directories, I would need to qualify the entire path to the file, but they're in the same directory. So I can just specify the file name. And I believe I named it spam sms.tsv. Now read CSV by default is going to expect the data to be in CSV format, comma separated values, but we have tab separated values. So I can specify that I want to use a different separator here by using the sep argument. And the separator I have is tab, so /t for tab. So that recognizes tab separated files. And we also noticed when looking at the file that we had a lot of rows, but there was no header row. So there was no row that gave header names for the two columns. So I'm going to specify those names here using another argument to read CSV. And I want to give it the names label because that was the data in the first column. And then I'll just say text as the data in the second column. And this needs to be a list. So when each row is separated by tabs, there will be two items because that is what the data looks like. And I want to give the first column the header label and the second column the header text. So at this point, my data should be loaded into a data frame. If I just say print df here, let's take a look at what that looks like. I'm going to go ahead and save this. Open my command prompt and execute this code. I named my program sms.py, so I'll execute that. And this is what the data frame looks like. So when I just print df, when I just call print on a data frame, by default, it is going to print as much as it can fit into a particular shape. There is a way that you can modify that. We won't do that right now, but it just kind of gives you like a snapshot just so you can see a little bit of what your data looks like. So it's showing me the first few rows, the last few rows, and then as much as it can of the columns. If there were more columns, they would be truncated here. So you see the triple dots showing you that there's more rows in between here, and there's more to this column here. But that just gives you kind of a snapshot view of what Pandas is now storing in a data frame format. So we see Each row was given an index. And this is something we could have specified, but because we didn't, the default is to just index each row starting with 0 and incrementing by 1. And then we see our label column and our text column. And then we also see that within our data frame, there are 5,572 rows and 2 columns. So that's just a quick way to make sure that we read in what we expected to see. So that was with printdf. If we want to explore the data further, so here we want to explore our data. So we printed it just to make sure that everything looked like we expected it to look like. Pandas has a couple of commands that are easy and quick to run to explore data. For example, I can say df head, and that will just give me the rows at the top of the data frame. Clear this. So if I execute df head, this code with just df head, I am by default getting the first 5 rows. You can also specify how many rows you want to see here. So if I change that to 15, run it again, now I'm getting the first 15 rows. So you can leave the argument out and the default is 5, or you can put in the number of rows that you want. I can also explore with looking at the tail of the data. So that would be the last few rows. And there again, the default is showing me the last 5 rows in my data. And another thing that I really love about pandas is the describe function. So the describe function, well, let's just run it and look at it, is a quick way to get a description of your database. Clear that. Sorry, not your database, your data table or your data frame. And what did describe do? So describe showed us that we have 2 columns, label and text. The count of values in each column is the same, 5572. So that already tells us something about our data, that we do not have missing values in our data. There is the same number of labels as there is text. Tells us how many unique values there are. So there are 2 unique values in label. That's what we expect to see. We expect it to be ham and spam. And so that tells us again that our data values are clean for that column. We only have the 2 values we expected. And then for unique on the text, we see that the number of unique SMS messages is 5169. However, there's 5572 text messages. So that tells us there's some duplicated text messages in there. So we might think, well, we should probably remove those duplicates. And then it gives us the top. So the top value, ham, and the frequency, ham occurs 4825 times. And so if we take 5572, subtract 4825, then we know how many spam messages we have. And here, the top SMS message is, sorry, I'll call later. And that appears 30 times in our data set. So we might want to filter those out. We might want to leave them in. A lot of the decisions on data pre-processing are really based on what you're trying to achieve and what you know about your data set. But just using describe, we were able to get a lot of information about that text data. If we have numeric data, describe would do something entirely different, and we'll look at that in another project. So we looked at head, tail, and describe to learn something about our data. Now let's see what else we can do. If we wanted to, if we were worried, so let's do some data cleaning. So if we're worried about there being missing values and we simply want to eliminate any rows that have missing values, we could say df.drop_NA. So NA means a NaN value or a null value in a cell. And drop NA is going to drop all rows that have a null value in a cell. When we call drop NA, that is going to return a new data frame with those values dropped, so we can store it right back into our existing data frame. If you wanted to do this in place, if we set in place equals true, then this is actually going to modify that data frame in memory in place and drop any missing rows. Now, we don't expect to see any missing rows from what we saw in df describe, but let's confirm that. So prior to doing drop NA, I'm going to print the shape of my data frame. To get the shape of your data frame, you can just type df shape. Shape is a property on a data frame. And I'm going to print the shape of the data frame. And so this will give you the number of rows and columns in the data frame. So I'm going to print the shape of the data frame, and then I'm going to do an in-place drop of any missing values, and then I'm going to print the shape of the data frame again, just to see if that picked up any missing values. So I save that, go over here and run it. And I see that the number of rows and columns remain the same, so I did not lose any values there. I didn't lose any rows, so there was no missing values. Another thing that I might want to do, so we mentioned that we had some duplicates. So how do we drop duplicates? Now, if you're wondering how to determine what these different functions are that are available to you, let's go back to the Pandas docs, because it's very important when you're working with Pandas to become very comfortable and familiar with the documentation. And specifically, if you go to the API documentation, you see the API reference here. Pandas API reference is laid out in such a way that you can just view all of the different methods available to you. We are working from a data frame. Pandas also has the concept of a series. So a series is like a single column in a data frame. Each of those are series. And series is like a list or an array, specifically a NumPy array. Pandas uses NumPy under the hood. So when we talk about a series that is equivalent or similar to a NumPy array, a data frame is an array of arrays. We want to look at data frame functions, and we want a function to drop duplicates. So you can scan through and see the functions, index, columns, info, values, size, shape. Shape is one that we used, data frame shape. And let's see if we can find something that says duplicates. There is a bit to scan through here, so if I don't spot it right away, I might just do a search for it. You see there's quite a lot of functions. You'll see if you're noticing a lot of math functions passing by here as well that are very useful. And here we go. So there's data frame drop, which is simply going to remove rows or columns. But then I saw data frame drop duplicates. I've lost it again, so let's go ahead and search for it. All right, so data frame drop duplicates. So this function will allow us to drop duplicates. And when you look at the documentation for Pandas, notice that it gives you the parameters that are available, a description of what each of the parameters are, and then the default values. So by default, drop duplicates has no subset. That means it's going to operate on the entire database. When there are duplicate values and you're going to drop, so if we have duplicate rows and we're going to drop one, we should specify which row we want to keep. Do we want to keep the first of the two duplicates, or do we want to keep the second? The default is to keep the first, but that is something that you can change. In place, false or true. So we saw in place before. In place by default is false, which means that when this function runs, it's going to return a new data frame with those duplicates dropped. And then we can simply store that in another variable or the same variable, or we can set in place equal to false to drop the duplicates in place. And ignore index is set to false, and you can also change that to true. So if it's true, the resulting index will be labeled, and the default is false, so it will not reindex the label. So I think we just want to keep all the defaults and just try drop duplicates and see if we lose any files or any rows. Drop duplicates, I'll leave in place equal to true. So after dropping duplicates, we see that we did, in fact, lose some rows. So we started with 5572 rows. After dropping duplicates, there were 5169 rows. And this makes sense because if we look back at our count and unique for the text column, there were only 5169 unique values, which told us that there had to be some duplicates. And that's exactly what we see using the drop duplicates. So drop duplicates helped us clean this data by removing duplicate rows in the data. Let's move on. So there are other things that you may want to look at and confirm when you are working with your data. But for now, I think that the duplicate rows were the only immediate problem we saw in this data set. So let's continue on from there. I think we're done cleaning for now. We did not have any missing values to deal with. If you have missing values, there's a lot of things you can do there. You can interpolate, you put averages in, you can simply drop rows with missing values and so on. And again, it depends on your data and the nature of your data and what you want to keep and what you want to lose. But always pre-processing your data and cleaning it prior to doing your analysis. Those are steps that you will always want to walk through. All right, the next thing we want to do, since we have text data and we want to apply a machine learning model, we want to convert this text data into a vector that can be easily fed into a machine learning model to improve the performance. To do that, we are going to use a vectorizer available in Scikit-Learn. So we'll start using our Scikit-Learn library. And the first thing I'm going to import from Scikit-Learn, so when you install Scikit-Learn, it is actually called, so incidentally, you will need to pip install both Pandas and Scikit-Learn, or install them via Anaconda, however, whatever IDE you're using, but you will need both Pandas and Scikit-Learn. When you install Scikit-Learn, it is called Scikit-Learn. However, when you're referencing it to import, it is sklearn, shorthand. So don't let that confuse you. So from sklearn, we are going to import a feature extraction .text count vectorizer. So we're importing the method count vectorizer from Scikit-Learn's feature extraction.text module. And then once it's imported, we can use count vectorizer to actually do some feature extraction. So now at this point, I'm going to copy and paste. If you're following along, this code is available on the website, so you can copy and paste. So you're not waiting for me to type these out. So for the vectorizer, we want to use count vectorizer. And then we're going to call a method called fitTransform on our text column. You access columns in a data frame by putting the column name. This is one way to access a column of a data frame if you know the column name. There are other ways to access data in a data frame. For now, we know that the column we want to use is called text. And then you'll notice that this syntax is similar to accessing elements in an array. So this is accessing a single row in a data frame or a single column in a data frame by name. And we want the column text. So df text, we send that to the fit transform function of the vectorizer that we've initialized. And by convention, we name our feature columns with a capital X. This is just a convention that we use in machine learning. And then we name our target variable with a small letter Y. So you'll commonly see this if you're going through tutorials. If you see a capital X, that's going to be representing a set of feature vectors, and a small y is representing the target vector. In our case, our target vector is our data frame column called label. So we want to train a model that, given features X, it can predict the label Y. So Y being our target, X being our features. And in this case, we only have a single feature, and that is the text. And this is our target that we want to classify as spam or ham. Those are our target values. So at this point, we have extracted the feature, our single feature, which was our text, and we have extracted that into a vector. So this is feature extraction. And that just makes it our machine learning process perform better. The next thing we want to do is split the data into training and testing data sets. Again, I'm going to copy and paste. And again, these variable names are by convention. You do not have to use these variable names, but this is a common convention, and it tells you that we're splitting the data into a training data set and a testing data set. Sometimes you might also want an evaluation data set when you're training a machine learning model, but for now we're just going to split the data into training and testing. So we need some data set aside to test the model after we've trained it. So we don't want to train a model using all of our available data, because then we have nothing to test it with. So we're going to split the data. And Scikit-Learn provides a function for us called train test split that takes as arguments your data frame of features, a series of your target values, the test size, which here is set to 0.2, which might be the default. You can look at the docs for that. And this is saying reserve 20% of the data for testing and use 80% for training. Of course, you can experiment with changing this value. Random state is optional. It is not necessary. We could leave that off. But if you set a random state, then that means that each time that you run this training, it's going to start with the same random state. That allows for reproducibility. So if we want to train once and reproduce those results in the second time we train, set that random state. In our case, we're going to run the same experiment against different models. So if we're running the same experiment against different algorithms, then we want to set a random state so that each time we start over, it's starting at the same place. Otherwise, you're not going to get a fair comparison. So while random state is optional, we're going to go ahead and set a random state. And now we will have training and test data split. So we will have training features. So the percentage of X features that are available for training, and then Y targets for training. And then we'll have our smaller test data set also split into X and Y. So train test split did this for us. Of course, we could have done it ourselves, but there's some optimization that's happening when you use Scikit-Learn's train test split. So it's the preferred way to split your data. There are many classifiers available at Scikit-Learn. Let's look at some of those. We want to do classification. And you'll see a lot of algorithms that are available. So if we go to classification, we have linear models, linear and quadratic, kernel ridge regression, support vector machines, gradient descent, nearest neighbors, Gaussian processes, and so on. So there is a lot of different processes available, and we're going to just pick up a few of them. For example, we'll use naive Bayes. So Gaussian naive Bayes is a classifier that we can use. It's called Gaussian NB, and there's an example here of how to use it, which shows some example code similar to what we're doing here. So I just chose a few classifiers to work with. You can certainly test with other ones, but in the example code here, I have chosen 3 different classifiers to start with. I'm going to copy and paste that code. And I chose naive Bayes, logistic regression, and random forest. So multinomial MB, logistic regression, and random forest classifier. And I set these up in a dictionary because I'm going to run an experiment I'm going to run the same experiment on each one of these classifiers so that I can then compare the results. So I'm evaluating these algorithms to see which model is going to give me better predictions. They're again setting the random state to 42, and the number of estimators on random forest classifier is a parameter that you can set, and you can read the documentation for descriptions of the available parameters for each of these classifiers and the values that you can set for those along with the default values. And we'll just leave it as this for now. With our classifiers initialized, let's see what we have left to do. So we've set up our classifiers. We will create a function to evaluate the model, but first let's look at the training and evaluating. So let's start with iterating through our classifiers. I'm going to copy this code. So we have the classifiers. So with the Python dictionary, of course, if we call classifiers.items, that's going to return the item pairs for each one of these key value pairs. So the key is going to be the name of the classifier, and then the value is going to be the actual object that I instantiated for each classifier. So I'm storing them in the variables name and CLF. So CLF is actually the classifier model from Scikit-Learn now. So as I iterate through these, I will call the fit function on each classifier, and the fit function is actually called to train the model. So we need to send it training data. So the X training data, so that's our training features, and then the Y training data, which is our target variable. So with the training data, we are sending the algorithm a set of SMS messages and a set of labels, whether they should be labeled as ham or spam. So this is a supervised learning method, and supervised because we are providing pre-labeled data to help train the algorithm, to help the model learn. After we call fit on the classifier, we now have a model, so we can test the model using the predict method. In the predict method, we're going to send it the test section of the features. Of course, we do not want to send the labeled data, so our Y test, we don't want to send that to predict because the prediction should only get the input feature, which in our case is an SMS message, and then predict from there what it thinks the label should be. So that is going to send us back a list of labels that we are going to store in Y predict, so label predictions. And then we need to compare those predictions to what we know to be the actual labels from our testing data. So when we did our train test split, we reserved that testing data for training, or the testing features, and then the testing labels. So we want to compare these predicted labels to the test labels after asking the model that we trained with the fit command. We asked it to predict with our test messages, stored those predictions. Now we want to compare those predictions to the tests. So I'm going to create a function, evaluate model, that is going to perform that, and then it's going to store the results of that evaluation in a results dictionary, because I want to do this for each of the 3 classifiers. So in the results, I'm going to store it as a key of the classifier name, and then the result of this evaluate model function. So let's implement that evaluate model function now. And I'll just copy and paste it from the website. So remember, we are sending evaluate model the test data that we set aside with the test labels, and we're comparing it to the predicted labels that came from the actual trained model. So we have true and prediction. Within Scikit-Learn, there are methods that we can directly use to do that comparison for us, and we imported those metrics up above. So all we have to do for these metrics is send the actual labels for that testing data along with the predicted labels in an argument to the function, and that function will compute the metric that we're looking for. So the accuracy score function, the precision score function, the recall score function, and the F1 score function. Each of those we imported up above from Scikit-Learn. And for 3 of these, we need to specify that the label that we're looking for is spam. So we want to know if we are accurately predicting that an SMS message is spam. So you can look at the definition in Scikit-Learn in the API docs for each one of these different metric scores if you want to see specifically and precisely what they are scoring, and of course then see what the parameters and default parameters are, parameters with default arguments for each of these functions. Here we're just going to directly use them, and every time we call evaluate model, we are going to return a dictionary that has each one of these scores returned from calling each of these functions. And so we'll have a nested dictionary in results where the key will be the name of the classifier we used, and the value will be this dictionary of 4 metrics. So what do we want to do next? We have our training set up, we have our training and evaluation set up. Now we just need to output some of these results to the console so that we can see what the results look like. So let me make sure I didn't miss anything here. So we have our results. We are iterating through the classifiers and calling fit followed by predict, and then calling our evaluate model function. And the rest of these are just going to print some output. So the first method here is simply going to print the metrics. So iterating through our results for name and metrics, we can print the results. Let's go ahead and stop there and run that before we continue. Make sure everything's running properly here. Open my command prompt. Run my function. Might take a little bit of time. Certainly if we had a larger data set, it would take quite a bit of time because we're actually training 3 different models, one after another, and then evaluating their performance. So that last block of code that printed the results for name, metric, and results.items, we print results for, and then the name, and then we print the metrics. Accuracy, precision, recall, and F1 score. So you'll have each one of these 4 values for the different models that we trained so that we can evaluate and compare them. So to go one step further, let's actually write the code. We want to look for each model. We want to know which model did the best for each one of the metrics. So for each model and each metric, who's the winner? So which model gave us the best accuracy? Which model gave us the best precision? Which one gave us the best recall? And which one gave us the best F1 score? And the last bit of code here on the page does that. So I'll just copy and paste this, comparing the classifiers. We'll paste it into our code. And this is going to list the metrics and iterate through the metrics and find the best classifier by getting the max of the result for that metric. So we won't walk through this code line by line. It's available for you to copy and study. This is just basic Python, iterating dictionaries, iterating arrays, accessing values in dictionaries. We have a lambda function, an example of a lambda function here to assign to get the key for to get each individual metric in that nested dictionary. So I won't walk through these step by step, but I wanted to provide some examples of a little bit more in-depth Python for some of you who are learning Python at the same time that you're learning how to do machine learning. And the final output we see here is the best classifier for each metric. For accuracy, logistic regression was best. For precision, random forest wins. And for recall and F1 score, naive Bayes wins. So we can continue testing if we want to improve these scores. Well, if you look at the scores, I mean, they're pretty good. So our best accuracy, logistic regression gave us a 97% accuracy, almost 98% accuracy. So that's not terrible, but we might want to improve that. And of course, we may not necessarily get consistency. So things to do to improve this testing and improve our evaluation. For one, we can remove this random state. So every time we run it, it's starting at a different place. So remove the random state everywhere. Again, remember we kept this in here so that we could repeat the results. So we do want to keep a random state on the train test split. Possibly if we're going to use the same if we're going to rerun it, we can test changing the test size. So if we take out this random, then every time we do this train test split, it's going to get a different 20% of the data for the test set. So obviously we expect that to maybe give us different results. We could also change this to have, say, 75% of the data training and or 85% training and 15% testing, and so on. So you could try different values of this. You could actually put this, all of this code into a loop that loops through and tests the code again with different test sizes and see if there is a particular test size that works better. We could certainly try other classifiers. There are a number of different classifiers. And within each classifier, the classifier parameters, we can fine tune those arguments. So maybe if random forest is one that we wanted to look closer at, we could try random forest with different values on the number of estimators. And we could look at different parameters available for the other classifiers as well. So there's a lot of different things you can change to kind of fine tune the parameters and test and evaluate different models. And this is basically the process of determining which classifier is going to work the best for this specific problem, this data set, which one's going to be most robust. And you can continue expanding your code to test more variations on the classifiers and the parameters used within those classifiers until you find the model that gives you the best prediction for your particular data set. And then, of course, if you then decide you want to use that same model on a different problem, if the data changes, the performance of the model might also change. It might get better, it might get worse. And so you might have to start over again when you change to another data set. So typically you want to find a classifier that generalizes well to the data that you expect to use the classifier for. So what I would do in this particular instance with this particular problem is once I found a classifier that I thought did really well with this data set, with this spam data set, I might go and see if that classifier actually generalizes well to another spam data set. So get another data set and see if I get comparable performance results on the new data set. And if I do, then that means my classifier is at least generalizing well to those two data sets. And I can test on more data sets and so on. But there are also some metrics that we can use that determine whether or not a model is going to generalize to other data sets. And we can look at that in another lecture. But for today, I think we'll close and end with this simple problem of detecting whether or not a text message is spam.